But yeah, so I'm Chris Palmer. I put together the Pittsburgh Livecode kind of organization, which basically means that I have the Discord and the meetup for this stuff. And I basically have never really organized any of these events, and it just kind of sat there. And I was like, eventually, I need to actually make an event, get everyone together, and subject some people to some live coding stuff. And I guess for people who didn't catch it, a bit of my background is that I originally started college as a music major. I studied French horn as my instrument, and then after like 2 years of that, decided to switch my major to computer information systems, moved to Pittsburgh, and then was like, there's got to be a scene for people making music using code. It took me 2 years to find them, but I did find that there were some people in Pittsburgh doing that. Got super into it, and yeah, now I'm still really into it. Would like to kind of share it with people. So today I'm going to be talking about Sonic Pi. Anyone who wants to follow along, you can get started by going to sonic-pi.net. It doesn't have anything to do with Raspberry Pis, so you don't need to do that, or you don't need a Raspberry Pi. You can run this all on your computer. You go to that webpage. You go to somewhere near the bottom. There it is. Nope. It looks very similar to that. I don't know how to, oh, there it is. Yeah, here's the download. You choose your operating system, and then it downloads the application. So, to get started with Sonic Pi, this is basically what it will look like when you're getting started. There's a couple changes that I have on mine. Basically, some of these icons up at the top I have changed, so I'll leave them like that. Let me close this. I'm going to move this table back a little bit so I can sit here. There's basically a couple of different primitive, there's two primitive concepts in Sonic Pi that I'm going to be talking about today, and those are sampling and playing notes with the synthesizer. So this will be a good chance to see if the audio is working. So to play a sample with this, you basically just use the command sample and then give it a sample name. There's a bunch of these built-in samples that you can go to help up at the top right, go down to the samples tab down here, and they're organized by different categories and stuff. And like, here's all your bass drum samples. I think house is a good one. How about this weather? All right, so here, if I, on my computer, I'm hitting Command R for run. That's the shortcut for hitting this run button up at the top. And let's see if there's a sound. Okay, so you can see there, we did it! A lot of troubleshooting. No, I mean, that's, if there's not sound and you re-plugged in your interface, that's usually what it is. But yeah, just calling the sample command will play a sample like that. So now, if I were to try to make something like a kick and snare sound, it plays them both at the same time because there's no waiting time in between them. So you have to basically specify how long to wait in between. So you do that using sleep. There you go. That feels more the right tempo, but you don't want to write that over and over again. So we've got this live loop concept. Drum. I don't want to call that drum. I'm just going to call it D. And because it's Ruby, you have to specify, like, you have to use basically this do and end construct as curly brackets or bracketing to specify things that fall into a code block. And so the thing here with a live loop is it is going to, as you have this all running, it's going to continuously be looping this, and as you modify things, it will update them on the fly. So if I want to speed this up, I can do something like this. I think that, that feels very terse, feels like you have to really write every single thing you want to have happen. I like to do a lot of stuff that involves a bit of randomness, all that kind of stuff. So I would normally do something like, let's make a list called L, and then I'm going to say 16.times. Because this is Ruby. It's got this construct for doing a for loop where you can just take a number, do .times on the end, and it will loop whatever you have inside there that many times. I'll do L.push. This is going to be taking that, that list up here that I have called L and pushing a value to it. I'm going to then use a, this is a sonic pi construct called, or it's a function called choose. You pass it a list or an iterator or something like that. And I'm going to use these symbols, that's what they're called in Ruby, for the bass drum. What do we have? This snare sound. And then let's get a hi-hat sound. Let's see which of these. Oh no. Oh yeah, you can actually check what a sample sounds like by doing this. That'd be great. Thank you. I don't even know if that's the pizza. But yes, you can go through and you play any of these to see, you can find the perfect snare and hi-hat sound. What was that? Cat? Cats. Cats. I think that might be. I like the snap one. So I'm going to go hat, snap, and then close all my parentheses so it doesn't break. So now it will be, here, let me close this so it's more readable. That's still readable. 16 times it's going to be pushing a sample to this list that it will be randomly choosing from these three things. And to play that, I'm going to do, here we were doing a for loop that is a, you know how many times you want it to loop. Next, I'm going to be doing what would technically be like a for each loop. So I do L.each, do, and then I. So what's happening here is that we're going to be looping through this, whatever the state of that L list is, looping through each of those values, and then assigning that value to this variable I, which then I'll be using the sample command to play that sample. Got to remember to add the sleep at the end there, otherwise it'll fail, because if I do this, it tried to play it all at once, it's got this thread death error because you didn't sleep or sync the thread. So sleeping that will now do this. And yeah, so that is a random, it's randomly choosing those, and you get like something that sounds like a reasonable drum beat without a lot of effort. But if I hit it again, or if I hit run again, it'll just be that same loop every time, unless I can never remember what this is. So I just went to another one of the, down here are the different, what are these called? It has some weird name for it, but it's kind of like files, but they're not files. It's silly. Streams, I don't know. But this is, what was that?
Clipboard?
It's like a clipboard. Sonic Pi has a weird name for them. I feel like they call them like streams or something. But they're not tied to real files, which is painful. Because like if you save one of these or you load something, all it's doing is going to that file, loading it into memory. It's still there when you close and reopen it, but it's not attached to that file. There's no save like the current state of it or any of that stuff. It's a little weird, but I basically end up just copying and pasting all of my code snippets that I want to reuse into Obsidian, and then go from there. But basically, if I don't want to hear the same exact drum pattern every time, this is a Sonic Pi thing called use random seed. You can pass it any number you want. I'm going to be passing it the current time converted to an integer. And I think, if I remember correctly, the current time is milliseconds or something like that since the epoch. So turning that into an integer is going to be different every time I hit run. So. Changing the number of times that it's going to loop through this list. So I started at 16. Started at 16, so that would be like 16 16th notes. I changed it to 14 to try and have like a 70 kind of feel, and then ultimately 10 and then 8. Just to kind of show that as I'm doing that, rerunning it, it is recalculating all of that each time. So you have the ability to change stuff as you go. Cool. That is a lot of how I use Sonic Pi sampling to basically make drum beats and all that stuff. The other thing I wanted to talk about is going to be how to use the synthesizers in Sonic Pi. We'll come back to this, but for now, I'm just going to start over here. So the construct that you use, very similar to sampling, for playing notes is play. You can name notes to play in all kinds of ways. I'm going to have it just play at C4. Right now, it is going to be configured to play oh, hey, look, pizza. Play using a sine wave. Actually, this feels like a good time to break, because I just finished talking about sampling. Let's all get some pizza, myself included, and then we'll come back and talk about synthesis in Sonic Pi. All right. So, to get back into this, where I left off, we talked about all this stuff with samples, making basically a pattern that you can loop over. The next part is going to be doing a very similar thing, but instead of talking about sample, basically sample names and all that stuff to pass around and store in lists, we're going to be talking about notes and all of that. So, like I was saying, instead of the sample command, we use the play command for using the synthesizer. There is a C4 played with a sine synthesizer. You can change the synth. What is it? Synth? Yeah, use synth. And again, if you go over here to help, you can go to here and it will show you the different synths. If you click on one of those, which I think technically beat is the default one, but it's a pure sine wave. Let me see. There's a bunch of these things you can change about them. The notes, amplitude, yeah. Yes?
Can you talk about the general structure of like when you put in a do and an end and when you can put in between a do and an end?
Okay, yeah, so I would say in general, and I think the thing that's a little weird there is that it's like talking, do and end in Ruby act as basically code blocks. And do you mean specifically in like this previous example?
Yeah.
Yeah, so I guess in this live loop do and end, that's defining all of the stuff that's going to happen within one loop. So for every loop here, it's going to be doing another loop inside there. So I guess every time you see do and end, I don't want to say it's going to be a loop, because you could use them in other contexts. Because I guess when you're asking of like, what can you put in the middle of a do and end, I think it kind of contextually depends, but in this case, I'm looping through something 16 times, and I'm running this command 16 times. Or command, not really, but I'll call it command. So 16 times it's pushing something to this list. And in this live loop, because it is a loop, you can also define functions using do and end. So that's a case where it wouldn't be a loop. I don't really have any examples of functions prepared for that, but it's a code block. It's a way to organize code within a structure that can be reusable, I guess. Is that a satisfactory answer, or is there something?
Is this like what you typically use in performances?
Yes. Yeah, or I guess what do you mean this?
The do and end construction.
Yeah. And that is that is a Ruby construct, not a Sonic Pi thing. The language of Ruby uses do and end as like specific words for opening and closing a block of code. Because you can see if I get rid of this end here, and if I try to run it, it'll fail. Well, because it's missing that, but I know that if I get rid of one in here, there's a bunch of ways that you can get it to format all weird and stuff. Yeah, like if I get rid of the end of a parentheses or something, it'll try to format it weird and it runs out of, it's missing something to close it. But yeah, basically do and end act as parentheses. They're opening and closing blocks of code. But yeah, so back to this. You can try different sets here. Let me try square. And that's the C4 using square wave. So I'm going to leave that for now. To that, I'm going to do a similar structure as I did before. Make a empty list. Do 16.times. Do and so again, this is creating a for loop that is going to iterate through 16 times. And this time I'm going to be pushing. Again, using this choose function, which will randomly select something from a list. I'm going to define a scale. Let's go with middle C and go with major pentatonic, because everything will sound good. And if I go over here and pull up the language, I can look up scale in here. That's scale. So this will show like the different parameters that you can pass into this function. I'm passing it the tonic note, the name of the scale, and then you can also optionally pass it a number of octaves. You see here, none, octaves, 2. And if I run this, nothing will happen because I don't have anything playing. Also, if you want to debug things, you can use the command puts. If I run this, it will then display, here's all of the notes that are ending up pushed into that list. And I'm going to demo this real quick, and then I will be wrapping up my talk. So the thing to do here would be do another live loop similar to before. Here I'm going to call this melody. Do and And this is, I guess that is the thing with live loops. Like that is just the structure of what you're doing here. You're saying that this is a live loop called melody, and do is opening up the code block of that live loop, and end is ending it. So here I'm going to do a similar thing where I do l.each, do I, again, that I. Again, that is going to be iterating through each of the values stored in L, assigning those to I, and then I will play each of those. I forgot to add the sleep again. Alright, so that sounds pretty cool. Sounds like a music box or something. The thing about that, basically you have these parameters for each note that's being played. So you have attack, I'm going to make attack 0, decay, and so it's the whole attack, decay, sustain, release. If you're familiar with synthesizers, you're probably familiar with that. Basically attack is the amount of time it takes to get to the maximum volume. Decay is the amount of time that takes to get down to the decay volume, and then sustain is how long it stays at that volume, and then release is how long after the sustain of the note it takes to go away. I'm going to make decay 0, sustain 0, and then release is going to be 0.5. So I'm going to make that a little bit tighter. And you can put each of these on new lines to make it easier to read.
Can you have the attack, decay, sustain, release be like a function of I? So it's,
Oh yeah. Oh yeah. But that would be a function of the note that's being played. Yeah, so there I just doubled the speed. That is the least amount that, yeah, thank you. That is like a very basic way to get started with Sonic Pi and be able to make these, I think they're pretty interesting sounding things without a whole lot of effort or needing to really know a whole lot of different things with this. Thank you.
All right. Hello, my name is Yoni. My artist today is from Spinach. I'm going to be talking about algorithmic bending, which I define as exploring, distorting, and playing with algorithms to create art. And I've been doing creative coding and live coding over years now, and I kind of find myself continuing to come back to this idea. A lot of our folks taking algorithms from the real world, particularly from mathematics, and messing with them to create art. So first, I want to talk about like what I'm going to define as an algorithm. Because when I first learned what an algorithm is, it was kind of like a computer science class, I think, and the way that they taught it was that an algorithm is a set of instructions for how to do something. So for example, like set of instructions for how to make a sandwich. And I think that's a useful framing, but it's also limiting. It's very sort of limited to the way that we program on CPUs, which are designed so that they can only process and do one instruction at a time. And I think a more general way of thinking about algorithms, especially for this context, is just the way that stuff flows into, out of, and within a system. So let's take as an example the Pittsburgh airport. So there's kind of an algorithm embedded in the way that it's designed. And like, if you're like someone who's going to go on a flight, like you can't go and walk into this like white area over here, right? If you are a pilot, you know, taxiing your plane, you can't bring your plane over to this blue area because then you're going to break the airport plane. If you like, you can only get past security if you have boarding pass, right? So the design of the airport basically dictates how people, goods, planes, etc., move around. And one idea from like Livecoding, from the top lab manifesto that kind of resonates with this is Livecoding is not about tools, algorithms are thoughts, chainsaws are tools. That's why algorithms are sometimes harder to notice than chainsaws. So the question that I kind of encourage you to think about over the rest of this evening in this talk is, and I don't have a good answer to it yet, maybe like, we'll figure something out by the end of this, is like, how can we take the algorithm that exists with this airport and turn that into art? And like, just consider that question like as broad as, or as, you know, specific as you want. And I think there's like a potentially like optimistic and liberatory way, form of thinking that comes with the seeing everything as an algorithm, and therefore seeing everything as a site of study and exploration and play. So I'll talk about a few examples, or sorry, before I get to that. This idea of algorithmic bending borrows very heavily from two forms of external art. One is Livecoding and the circuit bending. So with Livecoding, the algorithms are coded in the form of computer code, as Chris was just showing you, and they're modified, and you know, as you're sort of performing and writing code to create music, visuals, movements of robotic arms, really whatever you want. With circuit bending, circuit bending, for those who aren't familiar, is you take an audio or visual device, open it up, there's a circuit board there that essentially is an algorithm dictating how electrical signals flow in that device and how that device works. And you take wires and knobs and things like that, and you basically wire the circuit board in various ways that it's not supposed to be wired, and use that to get sort of glitchy and unique effects. So I'll talk about a few projects from my work over the past few years, particularly Livecoding, more recently with circuit bending that get into this idea of algorithmic bending. So first, I'll talk about ray marching strategies. I talked about this at the Hybrid Livecoding Interfaces workshop last year. So ray marching is an algorithm for rendering photorealistic 3D terrains with shaders. And so this image on the left is kind of what happens when, like, basically I coded up like the terrain marching algorithm as it's sort of supposed to be to get something that kind of looks like a terrain. And on the right, the code is messed up, but the image that is output is still cool, right? So what I did with this project is I tried to break down ray marching as an algorithm and like break it down into separate, like distinct yet interconnected modules, and try to figure out like how to intervene in the algorithm. So a brief description of how ray marching works. Basically, what it does is it tries to simulate the way that light travels from a light source through a 3D scene like this one and to your eye, or like to a camera, right? Some kind of viewer. So you have a bunch of like different like modules things that kind of try to explore sort of how they can like mess with the algorithms, right? There's like the ray origin, which is and the way this works is like the kind of clever thing about this algorithm is like rather than taking the light source and simulating all of the different like light rays and like how they travel through the room, you're kind of working backwards from the source that sees the light, and like having the rays travel backwards through the scene to the light source in order to kind of figure out computationally what the scene looks like through a 2D screen. So I'll talk about a few ways that I kind of mess with this algorithm. So one is messing with the camera position. So rather than having like a single camera looking at the entire scene, having a bunch of different cameras throughout the scene, kind of compositing those perspectives. So you kind of get these weird like composited, like layered sort of images. Another is then like using the screen position to mess with the camera, because like basically giving each pixel on the screen its own camera. That kind of got some wacky outputs. Another is messing with the ray direction. So for example, like, instead of having the ray travel in a straight line from the ray origin through the scene, maybe having it go in like a sinusoidal line, or having the trajectory depend on the screen position or something like that. Another example is this paper called Livecoding Dynamic Systems that I presented at the International Conference on Livecoding last year. So dynamic systems is a field within mathematics. It's used to study a lot of different systems in the real world. And without getting into too much of the technical weeds, I'll define a dynamic system as a system that regulates itself, or a system whose current state determines its future state. A few examples, like in the summer here, you'll see fireflies. When they're blinking, they kind of sync up, right? So that's like the fireflies all like responding to each other. Right? One firefly sees that it's slightly off another firefly and it tries to adjust itself, then maybe overcompensates and tries to adjust itself differently. The other firefly, might then also adjust itself. So they're all kind of dynamically regulating each other. These fireflies, their blinking is like a self-regulating dynamic system. Another example is population growth, where like the current population dictates the future population, right? The more people you have, the more babies they make. The fewer people you have, the fewer babies they make. Kind of oversimplification, but these kinds of models are used in a variety of different fields. So now the question is like, how do we apply this idea of like self-regulating systems to Livecoding visuals? So the way that I did this is basically having like particle systems, and each particle has a position and a color, and those each particle's current position and color can dictate its future position and color. So I'll show a couple examples with these videos. So like, for example, you might have particles like green value influence how much it moves in like the forward direction, or how far it is to the right influence how much its red value changes, things like that. So basically having the color and the position sort of interact dynamically to get these kind of cool effects. So that's kind of taking this algorithm of dynamic systems and trying to like warp and mess and explore it to get these cool effects. So this is kind of a more experimental project, is Livecoding visual driven music. So I think like the popular paradigm with like the relationship between music and visuals is like audio reactive visuals. And there's a lot of like interesting questions that come up with like, how do you map a musical signal like to a visual one? So like in mathematical sense, one way of framing that is like going from a one-dimensional signal, right? Like music is, you can see it as like an amplitude changing over time, so it's one-dimensional, to a visual which is two-dimensional, right? And so in a way, when you're doing audio reactive visuals, you are adding information to your music signal, right? Because the music still is one-dimensional, you're adding information to it so that it can become something that's two-dimensional, right? And with visual reactive music, you're going the other way around, so it's like a compression of information. You're going from this 2D image, or like video changing over time, to a 1D signal that's changing over time. So I'll show a quick example now. I'm not sure how, I don't know if I'm hooked up to the audio, but so you might just have to, okay, this essentially, you can be hooked up to the audio. I should like the, okay, so it's not super loud. Yeah, so what's happening here is the mouse position. I don't know if you can see the cursor here, but see as I'm moving the mouse to the screen, and the position where the mouse is, I'm just going to turn this down so that you can hear me talk, the position where the mouse is, the color at that position is then fed into like the code that generates the music. So that's kind of one way of like sampling throughout like the visual space and then translates the music. I'll do a little bit of like messing with the visual and see if that can trigger some changes in the music. Still kind of work in progress, but kind of one of the first things I went on was like using the mouse to kind of get a sample of the visual and then feeding that the color at the mouse's location to the music. So if anyone has ideas of like other ways they can map like visual and audio, I'm curious to hear. So then kind of getting to the circuit bending part, so this image on the left, that is an HDMI to composite video converter. Like HDMI is the video format that this projector is currently taking HDMI from the computer. It's kind of like the modern digital form of video, whereas composite is just like a single channel analog form of video that is kind of older. And so the image on the right is what happens. So I opened up this converter, that's the circuit board underneath it, and then you see there's that knob, that orange knob, that's connecting 2 points on the circuit board, and then when I turn the knob, it basically gets some glitchy stuff, so it's connecting those 2 points. This is my current patch. Maybe I'll do a, I think I can do a quick demo. So part of the goal of this setup is to be able to mix between the code that I'm writing live that's producing the visuals and the visual itself. So I'm using this mixer. This is an Anirol V4 video mixer, which is pretty interesting. It's from 2002, which is kind of right on the cusp between analog and video, analog and digital video formats. And so this contains elements of both analog and digital, but it takes these analog inputs, these yellow composite cables, as input. So one of the inputs is just the visual that I'm making, and then the other input is computer screen. So this is the code that I'm writing to produce the visual, and I can do fun things to mix between them. I can do effects. So now I'm mirroring the code. Doing a little color thing on the visual. So those are some fun effects. And then I'll just turn those effects off. And then the computer screen, so this part is the code and all that, that's passing through a few of these circuit bent converters. And we can come up during the demo or during the performance part and play around with it. But so this is that HDMI to composite that I showed the slide earlier. So as I turn this knob, we got cool glitchy stuff. Basically, turning the knob is breaking the converter, and then turning it back, and it's resurrecting it. So this is RCA, like a composite to VGA converter. And instead of using like a knob for turning it, I didn't have enough knobs. But my girlfriend works at the city textiles lab and works with conductive yarn. So I had this conductive yarn that could work as a resistor. So like pulling it basically like decreases the resistance and like gets crazy and stuff. And a similar thing with this next converter, which is VGA back to composite. And so yeah, there's like a whole bunch of different knobs to kind of play with, and that's basically it. Does anyone have any questions or any ideas on how to make our thinner or algorithm?
That last one, the threads is a lot more like tolerant to fault. Like HDMI adapter time shattered that pretty quick. Whereas this one kind of held on.
Yeah.
Why is that? And how?
Yeah. So
it's not just that.
Yeah, I mean, I'm not like an expert in this, but I can, like, so HDMI is a digital signal format, so like all the signals are basically have to be like either like a specific high voltage range or a specific low voltage range. And if it goes outside of that, then like it doesn't know what to do with that. Whereas VGA is an analog format, so you can basically whatever voltage you give it, it'll figure out something to do with it. Like it's not constrained to the digital ranges. Like digital lets you be kind of precise and fast, but it's a lot less like fault tolerant.
So were you talking about like a knob and they like that completely? Yeah, I've got to guess that might be something to do with that knob being like linear or
Yeah, I mean in terms of like there's like there being like very short.
Yeah, there's a very specific point where it's like
yeah. So that's really because the maximum resistance in this knob is like so like most of the space in this knob is nothing. It's like very high resistance. And then once you get to like the 200 ohm range, then it starts doing stuff. So I got it like a bunch of smaller potentiometers to then you kind of run through the whole range.
Gotcha.
Does that answer your question?
It's because digital is binary, ones and zeros. Analog is like the entire range of everything possible. So it's like either the ones and zeros are getting through, or like, you know, like this little wisp of like an electronic signal. It's just like more to play with, I guess.
Maybe during your performance exam. Yeah, but there's another talk, so yeah. Maybe students talk about title. All right. Yeah, yes.
Hi everyone. My name's May. I do music as rock on valve, but I don't release anything whatsoever, so I'm not included here. But here to talk about TidalCycles for live-coding sound. So here's my narcissistic slide talking about. I first came across like live-code music stuff in 2016 by this EP by Bell, and he like still holds up. He doesn't use Tidal, but he made his own language. Via that, I tried to get into various live-coding things, Tidal and Maltsman, but it was pretty hard to install. Especially back then on a Windows machine. In lieu of that, I was doing other non-live stuff. I like playing around in VC Rack, which is just a way to do modular stuff on the computer. I really love playing with the Chaos Pad and just having it resample itself. You have pretty cool stuff with that. I did bass drum in high school, marching band. Other noise things, pots and pans, that sort of stuff. In 2021, I tried to pick up Tidal again in earnest with a friend with a band in STEM. And that was a lot of fun. She played with gear things. 2023, I got to talk about Tidal at a modular synth meetup. So if any of you are modulars there's a lot of resonance there. It's a very different paradigm, but you can do some of the similar things in terms of complexity. Nowadays, in Pittsburgh, I've mostly been livecoding. Well, various people around town, not stuff, but also at Boyle, the Open Improv Lab at the MIT, which is every other Monday. Alex goes there a lot. But yeah, you also get to come out just to play. It's very inviting, and so it was a good environment for me to play live again. I also do other non-sound work, Hydra, E5 Live, another fun one. Yeah. So a little bit about our title. We're not talking about TidalCycles today, actually, because TidalCycles broke on me yesterday. Literal worst timing. Luckily, TidalCycles is one of a species of several languages called Uzu languages. It's kind of a more new term to me. But basically, TidalCycles is the main specific language for mostly livecoding music on top of Haskell, which is general purpose language. Strudel is the port of that for JavaScript, and it runs in the browser. So the install and that sort of thing is a lot more forgiving. So it's maybe a benefit that TidalCycles broke because it'll be a lot easier for you all to try Strudel, I think. And there are several other user languages that have certain language preferences. There's Vortex, which is built on Python. There's a whole list, which I can send to you all. But Uzu is just from Uzumaki, it's Spiral. Strudel is Spiral in German. TidalCycles, obviously, Spiral sort of thing. Also, this doesn't necessarily have to be about live coding, like doing a live sort of performance or an algo rave necessarily. That has kind of like a live improvisational sort of thing. Mostly when I'm playing with TidalCycles, I'm alone in my room and I save the files for later. So it's kind of a compositional tool in my head. But it's, you're using code you're evaluating code live to do musical things, so musical output, I guess. And I say sound in order to be fairly broad because not everything that I make is musical per se. But you don't need to make sound either. You use Tidal to do visuals and control robots. I think Yoni talked about choreography, which is another area. Lots of things you can do with stuff. I'm not going to talk about too much history today, but there's lots of interesting things to dive into as far as the history of TidalCycles. It goes back to 2009, presented by Algorithmic. He's a super nice guy. Has helped me a few times on the Tidal forum with some debugging things. Super active in the community, but there's lots of fun history inspiration from something called the EOL processor, I think it's what it's called, which itself has some inspiration from Carnatic Indian music. So one thing you might want to think about are issues of like cultural appropriation or like folk art or thinking about algorithms as this kind of like tradition that's rooted across like a longer period of time than just like tech per se. Algorithms are a much older idea. Leading is very old. Yeah, I'll link these papers and send it to you all. Okay, before I dive into the demo, the basic paradigm is that Strudel, TidalCycles, and the other user languages basically send patterns across time. But they don't really make any sound in and of themselves. Actually, they use other engines to handle that. So in the case of TidalCycles, most of the time that's Super Collider, which I think is the same for Sonic Pop.
Yep.
And in Strudel's case, most of the time that's the Web Audio API, which just is built into every browser, pretty much. But you don't have to use those for synthesis either. You can send MIDI or OSU, which is just fancy MIDI, over to your DAW for like a synth. So if you're like a synth musician, or if you're comfortable with the DAW or other kinds of music software, I think Livecoding integrates very, very well with those things. But yeah, that's pretty much all the slides, and let's get into the demo. So this is the Strudel REPL. If you want to follow along, if you go to strudel.cc, that's just that first part here. That's where Strudel is located. I would say one big advantage of Strudel is that the documentation is very, very good. And the same goes for Tidal. I think Tidal's docs are really good, but Strudel's really nice. If you take a look here, they have lots of pictures which kind of explain what's going on, which I think is super useful. But you all are not getting pictures today. I'll try to use my words. So,
Can you make the font a little bit bigger on that?
yeah, absolutely. How's this?
Yep, that looks good.
Okay, cool. So how do we make a sound? That's the first thing we'd like to do with Strudel. Again, this is built in JavaScript, so we can use a function which we can call with a function name. In this case, it's sound, and then a pair of parentheses. So you have sound, parentheses, and then the sound function expects the name of some sound. In this case, we want to give it a sample. I'm going to give it a kick sound. So this GTSK is just the name of the sample I've input into Strudel. It's not built in. Strudel lets you upload or import sounds into it, which is really nice. But there's tons of built-in samples as well. There are some drum machines, there are synths, yeah, you can also do crazy stuff like fetch samples live or do like text-to-speech things. But anyway, we can evaluate this line using Control-Enter. Let's see, how does it sound on that?
We may have turned this all the way down.
There we go. Okay. The paradigm of Strudel and TidalCycles is there's a constant clock, right? It's always going. It's always going once a second, or however fast it is, right? Because we only have one sound conjugate, we're just getting 1 thing a second. Let's say we want something else, let's say a snare. We get that once a second, right? So the GTSK and this GTSS are actually one of several samples. You can see that we have 37 picks, 28 snares. So let's say we want a different one. We can define a different sample within that folder using index in 2 different ways, basically. One is using the mini notation. Using mini notation, that's everything within the quotes. Quotes are not a string, they're mini notation in this case. This is going to be the same in TidalCycles, by the way. So if we evaluate this, in Strudel, it just evaluates the bottom line. So even though I didn't comment out line 5, it's no longer relevant. So now what this is doing, using :2, is selecting the 3rd sample within the kick folder because we start at 0 or 0 index. Other way to do it is using the end function. So in JavaScript, we can chain functions together using notation. So after defining a sound, which I'm aliased with S. So this S is the same thing as the sound above. test does the same thing. We can use N to change the index of the folder that we're selecting, right? So we're back to our kit. Let's say we want the second or the third kit within that folder. We get a different kit. Okay, what if we want more nodes? Well, again, the cycle is running constantly. So now that we have 2 nodes within our quotes, those take up their respective proportions within that cycle. Okay, so we have a kick at the front of the cycle in the first half, and a snare in the second half. So you get your 1, 2. And yeah.
Also, I do want to point out that this is essentially the same thing I did with the live loops, but look how much more concise that is with
It's very concise.
title. Yeah. No, that's what's great about it.
And I think it's pretty intuitive once you get used to it and play around with it. Now it's going to try to squeeze everything into one cycle, right? So if we have 5 things, we're going to get a 5, 4. I don't know music terms, but we have 5 notes in the cycle, right? We're selecting a kick, a hat, a kick, snare, and a percussion. Okay, so within our mini notation, we have subsequences. So let's say for this snare, right, it takes up a fifth of a cycle, right? 5 pieces of a cycle. The snare hit takes up a fifth. Let's say we want 2 different things to happen within that fifth of the cycle. You can use square brackets, say, okay, replace that with 2 different events, the snare and the hat. Let's say we want both of those things to be snare hits. Just use ETS twice. One shorthand we can do that with the multiplication signal. So or just an asterisk, right? Sounds the same. Times 2 just means to do 2 of these within the same chunk of the cycle. That same proportion. You can use that asterisk on subsequences. So now we have 4 events within the fifth of a cycle. Because it's happening twice. Okay. Another denotation thing we should know are angle brackets. So angle brackets just mean 1 per cycle. Okay. So it's going to swap between hit and lap each cycle and it goes around.
Sorry, can you turn that down a little bit?
Yeah.
Yeah, that was hard to hear.
Yeah, for sure. So the angle brackets just means do 1 of these things 1 cycle, do the other thing another cycle, and just move between them. So for the first cycle, we're going to get a kick. For the second, we'll get a clap, and so on and so forth. Now let's combine them. We can stick the angle brackets and the square brackets in or anything else. So within this sequence, within the square brackets, we're switching between a snare 1 cycle and the other cycle. We're multiplying that into then we have even more going on. Again, you can be intuitive with this, right? Like you could design it as a composer, or you can just throw a bunch of square brackets and see what happens. Usually it sounds pretty good, I think. Because it's on cycle, right? It's repeating and it's all structured. So nothing's random here, but already we're getting complexity, right? Like if I break down here, the angle brackets that are determining the last fifth of the cycle, one of those are 2 hi-hat hits. One of them is the sequence that has a subsequence inside it. Another. Okay, it's getting kind of busy. How do we add rest? cut. So cut works like a classic drum machine where once another sample begins, the previous sample that was playing stops. So you just use cut one. So now you're not bleeding into each other now. It sounds a little cleaner.
What would they do?
Yeah, so each of these samples, whenever, let's go back to that, it's just playing that event in that proportion of the cycle, but it just fetches that sample and plays the entire sample, right, for the entire length of the sample. So if your tape is super long, or if you have a really long, like, sample entire song, this is a classic record, you play it without cut, and it just keeps playing, you can't stop it. Once the event happens, it's going. So you can cut back in, and now the sample stops once the next sample begins. Another way we can sort our samples is with flip. TidalCycles is called meetup. And this just you pass into the function proportion. So already, right, let's consider the tick at the front. This takes up a fifth of the cycle total, right? If we pass in 0.7, and multiply that fifth by 0.7, so now it's 7% of its original length. If we pass in 0.1, everything's going to be really short, right? But one is kind of the same as the cut one because they only take up their portion of the map. So the bass drum or the kick is only going to take a fifth of a cycle rather than its entire cycle length. Okay, what else can we do? Well, there's the speed function which changes the speed of the samples. Like 0.5. It's a little bit lower, but it's the same speed, just it's the same tempo, right? But the speed of the sample they're playing is the same. We change it to everything's higher. There are other audio effects we can use. We can use a low pass filter, which expects a frequency, and add distortion as well. That sounds kind of beautiful. And oh yeah, you can add any of those things, any of those parameters that we just talked about. The low pass filter, the clipping. So already it sounds like kind of crazy without a lot of work, right? We've only used the same concepts that we talked about. So it's just a pattern, right? We have our subsequence, which we're multiplying, saying once per cycle, switch between this number and that number. It's like, it's baby stuff, but I think it sounds great. So, yeah, the pattern. Okay, so we talked about effects, audio effects, but there are also effects that change the actual pattern itself. So one of those is red, which reverses the order that things are in. We're going other direction, going backwards. We can change the tempo that we're playing things in. That's fast. Again, we can pass that pattern. So go twice as fast, go half as fast, first as fast. Now this starts to be a little tricky to think about because, so for the first third of the pattern, you're going twice as fast, and that's slowing things down. And for the middle third, you're going half as fast. And it's going to just be intuitive rather than like intentional about what you're trying to do. just throw stuff on there. For example, hurry is another good function that combines the speed function and the fast function. So fast doesn't change the output, but it doesn't change the speed that the samples are playing. Hurry does both, so it's like things are speeding up or slowing down. So now we have a little bit more like mid-period than that. We can do math on any of these patterns. So if I put the dot to one of these mini notation or strings or whatever, we can perform a function. Mul is multiplication, so we're going to multiply all these numbers that are increasing speed by 0.9. We're going to add 0 one cycle, and then 5 another cycle for n, and then multiply for speeding up the tempo, and down, and craziness. Okay, next thing I'm going to talk about is maybe the most important thing. It's a classic meme in the title section. C, jump spread. So we'll start with a simpler example because things are getting a little wild. Right? So what jumps does is it creates a copy of this. And it hands the copy and the original across the stereo field, one to the left and one to the right. And almost always this sounds pretty good. Like almost always, because you're left with like the same structures that you had, but it's reflective, right? So just expect some sort of function to be applied. So when you have in red, the second, the copy of that pattern gets reversed. Right? Jumps by is just a variation of jumps, but it lets you control how far that hand goes. So now bring it back a little closer to center.
Question.
Yes.
So there, can you pass in like compositions of functions like rather than just stored?
Yes, yes, you can. Actually, in this next one. So if we wanted to hurry, for example, you don't have to just rev. So we're getting a faster pattern and that's zero there. If we wanted to hurry and rev, right? We need to talk about arrow functions. So remember, jumps and jumps by expect some sort of function. We've been passing in rev and hurry. They're just the names of functions. In JavaScript, luckily there's a lot of coders here, but basically define a little function as one of the parameters. You can just use parentheses. This little function, which is also a parameter, will expect the parameter, the pattern itself as a parameter. So P just represents the copy, right? So 2P, we're gonna hurry it by 2 and reverse it. Sounds pretty cool. Okay, so we can create copies and superimpose those copies across time instead of the stereo field using off. So the first parameter of off is the proportion of the cycle that this copy is going to be adjusted. So the copy is now an 1/8 note ahead, or an 1/8 of a cycle ahead of the original. And those samples are playing twice as fast, or they have a higher echo width is a different version of off, which is a lot more flexible. It lets you define how many copies you want. You can also tell it how far away those copies can be, and you can give it a function like off. Now we have 8 copies. So in your function that you're passing into echo width, you can give it the pattern, but you can also give it the index, which is, in this case, just x, but you could use anything and that index is being referenced for the speed. So the first copy is going 1.5 times as fast, the second copy is going 1.5 times 1.5 times as fast, and it just sounds like that. Okay, this one, I think that this is just an example of combining more things, so you can echo it, but you can also juxtapose on top of that. So curly braces I use all the time. This kind of like unlock things a little bit for me. It's just really, really useful. Basically, it's take this sequence of things and let's a snare and a hat and cycle through this sequence of events for some proportion of a cycle. So we want 4 events per cycle. We want quarter notes, but we only want 3 things to happen. Or we want to cycle through these 3 events for those 4 notes. So go kick, snare, hat, kick, and then begin the next cycle on snare, right? We can use curly braces. So it's kind of hard to tell that these are quarter notes. So I can add another pattern using commas that just happens at the same time. That's kind of hard to do. So if we make this a sequence where P is happening at the beginning, and then let's see, 3 of those. So already you get something that doesn't loop every cycle, right? It loops every, I don't know, mathematically it's like n cubed, whatever, but you're cycling 3 things over 4 times. Anyway, if we play with that, you can do cool stuff, like in a lot. And if we go back to our original crazy pattern, and not very complex, but it's just the same stuff we covered. Very simple. Very simple way to achieve something that I think is pretty complex. As a demo, last thing I want to show you is that you can also do Hydra in here. Yoni was doing the same thing. Hydra.
I was going the other way around.
Yeah, the other way around.
Hydra.
Yeah, so they integrate really well because they're both built on JavaScript. Thanks.
All right.
Questions?
Oh, I'm gonna try the lecture.
Did you say there was a way to break this up out as opposed to just doing things in the browser?
Yeah, there is. So like I explained at the beginning, I'm more of a TidalCyclist than a structuralist, but it doesn't matter too much because documentation is really good. We go to learn, there's maybe an OSC section on the left, and it's fairly straightforward to configure like a mini input and a mini output. So this would send things to MIDI. Let's just try it just for funsies. Actually, it might take a while to find the right driver, but basically, as long as you pass it the right name of whatever's handling MIDI on your machine, you can send MIDI out pretty easily. Yeah, which is why I think this like integrates with any musician, even if you're not like a Livecoder or anything. If you have like a DAW sort of workflow or you use synths, this sends MIDI out like pretty easily. Yeah. Any other questions?
It seems like this gets very complex very quickly. Like, for me, I feel like I would get pretty overwhelmed by all those possibilities. So, like, what's your relationship with that? Like, how do you like handle the complexity? I guess.
Sure. Yeah, it's a weakness of mine too, for sure. I think I let things get complex, and then I don't know. There's some philosophy in the Livecoding scene of like letting things go and deleting stuff. So when something becomes overwhelming, just like do something else. Another thing, like if you're talking about like this last thing has a lot of stuff, right? A typical function used to quiet things down is degrade. So degrade, still kind of complex. Well, we'll still get the same complexity, but randomly produce events. So by 50%, there's a degrade function. Pass it a higher number. You get almost no events. So now it sounds like nothing's happening. Usually you can maintain some structure by having the degradation happen before any repetition or copying. So if I put degrade by before juxtaposing, there's a copy that's happening. Although the juxt is a little bit complex now, so if we just make it reverse, maybe that'll be it. I can kind of do that. We multiply the speed by -1. It's a little bit slow. Yeah, just degradation is one way to do it. That's typically one way. Also just moving on to the next thing. Another way also, I guess, is like commenting things out. So, we're back. It's easy to like get back to the previous state.
it's like weird things happen. To kind of that's the color version is happening. So that's yeah, you see how yeah, it's the one that's like it's the flash that's the one that's non-controlled. So you see how it says colorized here? This is negative. It's like kind of black.